All right, hello everyone. Let's start off by talking about your practice tests or your assignment submission. So just want to know, have any of you guys tried doing submission, and were you successful? Do you have any trouble with getting it into Word doc? We're all trying to figure things out. So how was your experience? Anybody have success or tried it, it worked, or tried it, it didn't work?
It worked for me.
It worked. Okay, can you talk about how you went about doing it, just in case other students are wanting to try your method?
So I just made a Word document and then put it, and then wrote like my name and was there a, I didn't know there, sorry,
Oh,
was there a
yeah. So the assignment was this one here.
oh,
So
okay.
this, okay, so this is under assignment tab of your teams, of the teams page. So I think there's yeah. So this is how you're going to be pulling the test, and then from there, then I wanted students to be able to write on this, either by printing it out, writing on it, taking a photo, and then trying to find a way to get it into a Word document, or putting this into OneNote, writing on it, and then getting it into a Word document. So that's what I'm hoping to do, because when the test becomes available on Friday, one way or the other, you're going to have to be able to write on a piece, or you have to be able to show your work in one form or the other.
It's okay if it's a photo in Word though, right?
Yes, yes. I think that is probably the best way to go about doing it, especially if you're having to write it on a piece of paper. But if it's in Word, I think the only thing, yeah. So when you do that, just double check and make sure that it is legible and I'm able to see it and that's not blurry, or if it's not it's not too zoomed out, or things like that. So anybody else have able to try that and able to have some success there? The previous period, they were saying that there were some issues with Word document. They were able to get into a Word document, but then they couldn't save it, or it wouldn't submit in Teams as a Word document.
Yeah, that's what I was having problems with in my last period.
Okay, can you detail what error you're getting?
So I finished doing my assignment on the Word document, but it wouldn't let me save it to my computer. And if I did get to save it after like half an hour, then I went back into Teams and it wouldn't let me turn it in.
Huh. It would. What error message would it give you if you try to do that? It just wouldn't.
The team, yeah, it just wouldn't submit. It would just either take a long time to submit or it wouldn't submit.
Huh. Okay.
What I did was I just took a picture of it on my phone and then posted it on Teams there.
Okay, so when you posted it, it's not a Word document then. It's just a JPEG file.
Yes.
I see. Okay.
There's like another way that I did it, like when I turned it in, because I didn't do it for your class, but I did it for chem because I had this. The way I did it was I downloaded Word on my phone, and then when you download Word on your phone, you can sign in with your like FCSTU Gmail or your FCSTU
account,
and then you do like a new Word doc, and then you just put the picture in through there, and then you can save it into your OneDrive, and then you can automatically go into Teams, and it will be there if you're trying to put something in from the OneDrive.
I'm also wondering whether this is possible, where you use the Word doc. You use the Word doc app on your phone, and when you do that, there's an insert feature, and you can insert a photo into that Word document. And I'm wondering whether you can just take that Word document that is sitting on your phone and just submit it directly through Teams, through your Teams app on your phone as well. I'm wondering whether that will work.
What I did was I just saved the document, and it went automatically to my OneDrive. And then when I went onto Teams and I tried to attach the file, because Teams is attached to your OneDrive and your FCSTU account, so
Right.
it was already on there, so I just clicked on it and it went in.
Okay. So it looks like that is able to work. Okay. Yeah, see if you guys are able to get that Word doc app on your phone. If you guys can try that today, that would be great. And then I need to push out the deadline to tomorrow because I have the close date on that assignment to be today, but I should do it tomorrow in case students still have issues and need to try a different method tomorrow. But if worse comes to worse and you just can't get into a Word document on Friday, you can just submit in any form. It just take me longer to be able to grade, but I mean, ultimately you're not going to get points taken off because you're having trouble getting it into that Word doc. But ideally, that would be best for me in terms of grading. So, but hopefully we can give that another try today and see if we can work our way around issues today and tomorrow. Okay, thanks for sharing, guys, and hopefully we can have more success tomorrow or today after you guys try it. Any other questions about submitting this practice assignment? Let's talk about your test for Friday, and I want to give you, and then this, I'm probably going to reload this again because I added some more notes to it, but this sheet is on under today's date on my website. So September 2nd. I have this as a link, test topics. I just wanted to give you kind of help narrow your focus of study so that, because my review sheets kind of jump from topic to topic, but I want you to know exactly what to study for going into the test. So first up, all free response, there's no multiple choice, okay? You're going to be asked to evaluate limits algebraically. So it could be limit as x approaches 3, it could be limit as x approaches infinity, it could be limit as x approaches 3 from the left. But we know with real numbers, we always plug in that real number. If you see a one-sided limit, you also plug in that real number, no decimals yet. And if it's infinity, we have a different approach, right? With infinity, we compare degrees between numerator and denominator because we have a completely different way of dealing with infinity when we talk about limits. Now, if we if we plug in that real number, and if we get a 0 over 0, we know there's a hole in the graph. And when there's a hole in the graph, we have different types of problems that exhibits holes. And with holes, we know we have to eliminate the hole. The limit exists, but it's kind of hidden from our view at this moment. So the way we identify and find those common factors so we can eliminate the hole, one thing is going through factoring method, get that numerator to clean up so we can cancel out between numerator and denominator and reevaluate. If we see radicals, we're going to go through conjugate method, get the numerator to match the denominator factor. And then with the complex fractions, sometimes we have to go through common denominator. So we're going to clean up that numerator fraction, get it down to one denominator, one fraction, and then we can find that common factor to cancel between numerator and denominator and then reevaluate. Third type is being able to identify limits and order pairs from a graph. So if I give you a graph, can you identify the properties that I ask you for? So this is one of the first things that we did with the first week of school, where I gave you a graph and I gave you a bunch of properties or order pairs or limits, and they have to tell me whether the limit exists or doesn't exist. Or if I ask you for an order pair, you tell me that order pair is undefined or whether the order pair exists. Okay, so being able to evaluate the limit in the order pair if I give you a graph. Another type is being able to sketch a function given limit properties. So this is the practice problem that you were to submit on for the assignment through Word, where I give you a list of properties, and then you're going to create a graph out of those properties, a function out of those properties. Using continuity conditions with the piecewise function to determine continuity and discontinuity. If there's a discontinuity, categorize it. Okay. And we did this yesterday, right? With the piecewise function, we went through the conditions. So we'll practice with that again today. Applying intermediate value theorem. So intermediate value theorem says we're given a function, and can we guarantee that this graph is going to cross through or touch a specific y value? The way we determine that is we first have to establish that the function is continuous on the closed interval. And then we take the endpoints that the problem gives us and we plug it into the function to determine where the y values are. We want one y value to be below the target y value. We want the other y value to be above the target y value. That way, we're going to be able to see and convince ourselves the graph is going to have to connect between our two endpoints, and it has to cross through that value somewhere between. Or we have one endpoint being above and the other endpoint being below, and that way we can visualize a graph going through that y value somewhere between. Now, resources that you get to use on the test is the summary sheet that is, okay, the summary sheet is on, if you look under yesterday's list of links, you're going to see that summary sheet. So the summary sheet looks like this here. It's got the algebraic steps for evaluating limits approaching real number. It's got the steps for infinity and negative infinity for compared degrees. It's got the continuity conditions spelled out with the types of discontinuity. And then it's got IVT steps as well. So you can print that out and you can have that as a resource as you take your test. Anybody have issues finding this? It should be next to yesterday's notes. I think it says like concept sheet or concept summary sheet. You can also use a calculator. Friday morning, I'm going to have a morning review, just answering any questions that you guys have, and we can also go through worksheet 3. I have a link to that under Friday, if you look on Friday. I'm going to hold the morning review session in the help sessions channel, calc help sessions channel. You guys should all have it. Let me know if you don't see that channel. Maybe you maybe you entered into my class a little bit late and I don't have you. If let me know, I can add you to that channel. Or sorry, add you to that Teams page.
Do you still have one every day, like before school?
Yes, yeah, I still have one every day, 7:45. So yeah, you can come to the tomorrow morning as well.
Okay.
So this Friday morning review session is going to be, I'll record it. It's really early because I have a meeting at 7:45. So, but I will record it. Some students were asking, what if I want to go through this review session earlier than Friday? Is there a recording for that? And yes, I have a pre-recorded video from previous years. So I will put that link, that YouTube link, next to worksheet 3 under the Friday date. So if you just scroll down on my website to Friday, you can, if you want to work through this beforehand, or if you want to watch the video of me going through it. But I will also have a live recording that you can find under the Help Session Teams channel. There's going to be 9 questions total. All right, any questions about the test? All right, let's go to our test review. And I'm going to be doing we didn't get a chance to do this yesterday, so we're going to do the review worksheet 1 today, and then we'll do the review worksheet 2 tomorrow. Here we have a piecewise function. Okay, so let me just maybe give a visual. Okay, this is not going to be accurate here, but what's happening is we have this graph here, and this graph is all kind of all over the place. You got x plus 5 to the left of 2. We got an ordered pair that's sitting at 211. We got the 2x minus 1 between 2 and 5. Again, you don't have to graph it. I just want to have some visual to kind of reference things. You got 20 sitting at 5. So that's an ordered pair all the way up here. And then you got x plus 4. That's between to the right of 5. Okay, maybe something like this. Okay, we should be able to do all this without a graph, but I think it's maybe if we're having trouble seeing something, I can reference the graph and kind of convince you how, where things are, how things are lined up. Okay, so limit as x approaches negative infinity, we have to first just try to figure out which branch is going to be the one that's headed towards negative infinity. And if we look at our list of conditions, everything less than 2 is going to be within this x plus 5 graph. So negative infinity must be along this x plus 5 graph. So let's go ahead and replace g of x with x plus 5 because this is the branch that we're looking at here. And what step do we take when we see infinity? When we're approaching infinity and we're trying to do it algebraically, what's our method? What's the first thing we want to start looking at, or what's the first thing we want to do? Or how do we deal with limits approaching infinity on Monday? What do we had to switch gears, right? We don't plug in the number. What do we do?
Isn't it like that 3-step thing?
Uh-huh. And what's that first step that we do?
I'm totally forgetting. I just know it's a 3-step thing.
Okay. Yeah. We compare degrees, right? We compare degrees between numerator and denominator, and then the result of that is going to help us decide which option to choose. Okay. Oh, sorry. Someone was speaking. It sounds like you're breaking up. So numerator and denominator, right? But there's no denominator, but we can always put the numerator over 1, right? So we know we're comparing degrees. And what can we observe here? What happens when we compare degrees? Which category does this fall under?
They both have the same degrees.
Do they fall under C because the lower one doesn't have an X in it, right?
Yeah, so technically, maybe you're looking at the coefficient, thinking that's a 1 and 1, but really there's a hidden variable here, and it's x to the 0 power. And this is x to the first power. Right, so the variable disappears because it's to the 0 power. So the numerator has a higher degree. So when the numerator has a higher degree, it falls into the third category, which means that the limit doesn't exist, but we got to choose between two options. It's either positive infinity or negative infinity. And we know that when we're down to two options, we always have a test case. And because we're approaching negative infinity, we want to choose a value in the direction of negative infinity. So let's choose a number. So if I plug negative 100 in for x, I get a negative number. And I see my graph kind of resembling that as well. Okay, but I want to focus on being able to arrive at our answers without the use of a graph, but I can reference the graph if we're having trouble, making that connection. All right, limit as x approaches 2 from the left side of 2. So we want to approach 2 from the left side of 2. That means we want a graph that's smaller than 2, that has a value smaller than 2. And if we look at our restriction, value smaller than 2 is going to be this x plus 5. And so we're still on the x plus 5 here. Right. And if I want to evaluate the one-sided limit, we always plug in the real number, right? We don't do anything with decimals. We always plug in the real number and we get 7. So if you had the graph in front of you, you would be picking a point to the left of 2, which is sitting on the x plus 5 graph. And then you would move towards 2, and then you would see that the y value is headed towards the graph is headed towards a y value of 7. Okay, but we're practicing being able to make find these values, without the graph, right? We're trying to see if we can do this from a numeric algebraic standpoint. Okay. If we're approaching 2 from the right side of 2, that means we want values a little greater than 2. And we see values slightly greater than 2 is going to be between 2 and 5. So the 2x minus 1. Again, we plug 2 in for x. We get 4 minus 1, which is 3. And so visually, what could happen is we're picking a point slightly to the right of 2. And that is sitting on the 2x minus 1 graph. And then we're moving towards 2. And it's taking us to a y value of 3.
I have a question.
Yes.
Just I'm a little bit confused about once you get the which one you're using, like the x plus 5 or the 2x minus 1. I get that, but I don't understand. I know how to figure that out, but I'm not understanding how you figure out which one to choose, if that makes sense. Where it's
Okay.
where it says 11 and then x equals 2. What is that even?
Right,
What's
right.
the
Okay.
purpose of that?
Right. So when you see less than or greater than, that indicates that we have a connected part of graph that's going to be more than 1 point. But when you have 11 at x equals 2, normally 11 is going to be a horizontal line, but we're only defining it at 2. And so on the graph, it's going to look like it's just a point. But then the x plus 5, where x is less than 2, it's going to be an entire graph, but it's only going to show where x is less than 2, so it's going to be cut off from this point forward. So we're only showing snippets of graphs because the restrictions is forcing only a portion of the graph to show up. But when you see equal sign, that just indicates that it's just a point, a random ordered pair that just happens to sit on the graph.
Okay.
So when we do limit as x approaches 2 from the left and 2 from the right, we always have to look at the connected parts of graph. And the connected parts of graph is going to have to always be part of these segments. And the segments is only going to exist when you see these less than, greater than notations. We don't consider the order pairs for limits because there's no approach involved, right? There's no connected parts for us to approach because if it's a random point, it's just an island. There's nothing that we can gather about the approach with order pairs.
Okay, thank you.
Okay.
And then I have a question also.
Yeah.
So where it says 2x minus 1 on the graph, shouldn't that be lowered 2 points? That way one of the points is touching -1, or does it just not matter?
Yeah, I'm not doing a very good job with my graph. I just want to kind of give a visual so that we know which function we're choosing. And technically we should be doing this without a graph, but I just want to have some reference points. So yeah, I'm creating this out of the blue.
Okay.
So yeah, it's not accurate.
Thank you. That's
Thank you. Now, what if we wanted to find a limit, the full limit as x approaches 2? What would you say is the full limit as x approaches 2?
Does not exist.
Okay, and why would you say that? Why would you not just look at this ordered pair and say, well, it's 11?
Because the ordered pair wouldn't be like, the graph would not be continuous.
Okay, good. The only time your ordered pair is going to match your limit is if we're dealing with a continuous function. And how do you know that this is not continuous? Is
Because
there
coming from the
anything?
left and the right, the limits aren't the same.
Okay, these have to agree, right? Maybe the graph looks something like this, right? From the left, from the right, it's approaching different values. The limit doesn't exist. There's a discontinuity. The ordered pair is sitting here, but the ordered pair is only going to be the same as your limit is if you have a graph that has no breaks. If the approach and the ordered pair is the same, then we have continuity. But even though f of 2 is equal to 11, that is not going to be the limit in this case because we have some surrounding information to help us conclude that I have a different approach on either side of 2, and if I'm not moving towards the same y value, my limit doesn't exist. Okay, limit as x approaches 5 from the left side of 5. So we want a value that is slightly less than 5, so maybe in the 4 to 5 range. So slightly less than 5, it's going to have to be on this 2x minus 1. So if I were to look at the graph, right, if I'm choosing a value to the right of 5, to the left of 5, I'm going to be sitting on the 2x minus 1, and I'm going to be moving towards 5. So I'm going to be plugging the 5 in for the x. So I get 2 times 5, 10 minus 1 is 9. Okay. Limit as x approaches 5 from the right side of 5. Values greater than 5, so I need to be sitting here. X plus 4. And here we get also 9. Okay, so my graph is not accurate here. But based off of this result, okay, we have limits from both sides of 5. So what would you conclude is the full limit as x approaches 5?
Would the full limit be 9?
It'll be 9 because we have a consistent movement from both sides. Okay, so my graph is way off, but I just wanted to provide some visual perspective, probably more like this. And again, we don't choose the 20 because the 20 is just an island. It's just sitting there. There's no approach, right? The graph is not moving towards that point. The graph is moving towards this hole, and that hole is at 9. Right, any questions there?
Wait, why'd you say it wasn't 20 again?
It's not 20 because we see that as we approach 5 from the left side of 5, right? If I want to find the full limit, we always pick points on either side of 5. So if I pick a point on this side of 5 and I move towards 5, it's taking me towards 9. If I pick a point on the other side of 5 and I move towards 5, it's also taking me towards 9. So the limit is about the approach, right? Even though there's a hole there, the approach is consistent.
Okay, that makes sense. Thank you.
Okay, good.
So is 20 just totally irrelevant in this whole thing?
It is irrelevant because it's not continuous.
Okay.
But if it were continuous, then Yeah, I mean, let's say this said 9 instead.
Okay.
Then it would match, right? Because the hole that's existing here is cleaned up nicely by this ordered pair.
Okay.
Yeah. Okay, good questions. Okay, limit as x approaches 6 from the right side of 6. We want to start on the right side of 5. That means it's going to be this one here, right? 6 to the right, that's going to be along this path, and this graph is on this x plus 4. Plug in 6 in for x, we get 6 plus 4 is 10. Infinity is a value greater than 5, so it matches this condition. And when we see infinity, we compare degrees, right? Between numerator and denominator. I don't have a denominator, but I can always put a 1 beneath it. X to the first power versus x to the 0 power. X to the first power wins out. So it's a third condition. My limit doesn't exist, but my graph is either going up to positive infinity or negative infinity. We do a test case, positive 100 in the direction of my motion of my graph. 100 in for x, that's a positive number. Positive infinity. As we exit the graph to the right, the arrow is pointing to positive infinity. Right, let's practice the continuity condition problem here. Similar to one that we did yesterday. So give you guys a minute. Can we step through the continuity condition using the notation spelled out by the definition? Can we find the C value? Can we find the order pair? Can we find the limit? And if the second condition fails, we know that we have non-removable discontinuity. If the third condition fails, we know there's a hole in the graph, so it must be a removable discontinuity. And if all three conditions pass, then we know our graph is nicely connected and the graph is continuous at that point. Okay, so see if we can start that, and then I will walk through it with you.
Is your Yang?
Yeah.
Is the test going to be structured in the format like the worksheets, or is it going to be different? Like, or like kind of like how you, like the first part, is it going to be part like that, or is it going to be like
Yeah. I'm gonna have some problems where you're gonna have to pick it. You have to pick from a piecewise function, and then once you have it down, then you got to decide what to do, whether plug in or compare degrees.
Okay, thank you.
Mm-hmm. And then on worksheet 2, we'll get some more practice with this type of a setup as well tomorrow. Okay, first step. Does the point exist? Where's our C value?
3.
3, right? Always given to us. You're never going to have to guess. Always should be somewhere in that restriction. This is the potential place where there's a disconnection and we want to test it at that point. Test our continuity at that point. Okay, which function do we plug into, first or second one?
The first one.
Yep, got that. We're looking at that inequality, right? There's an equal sign there, no equal sign here, so it has to. It's only going to live on this first graph here. Okay, second condition. Does the limit exist? So, can we rely on one limit statement or do we need two?
Two.
Okay, and why? Why do you say two?
Because they approach differently from either side.
Yep, and they're referencing different, they're along different graphs, right? So if we want to approach the limit from both sides, we're going to have to evaluate them differently, separately, because we have different graphs on either side of 3. So maybe the graph looks something like this. Again, not accurate. So you got x squared minus 2, you got the x squared plus 5, and we want to find the approach from both sides, so we want to evaluate them separately so that we know whether they're connecting towards or moving towards the same y value or not. So if we're approaching 3 from the left, that means we're picking a point to the left of 2. So that means we're along this path of this x squared minus 2. And then if we're approaching 3 from the right side of 3, that means we're starting at a point slightly to the right along this path, and we're moving towards the target. And when we plug in, we can identify where the target is for both one-side limit. If I plug in 3 in for x, 3 squared minus 2, that's 9 minus 2, 7. If I approach 3 from the right, 3 in for x, 9 plus 5 is 14. So what conclusion can we make based off of the one-side limits we found? Do we continue on to the next condition?
No, because they don't equal each other, right?
That's right. In order for the full limit to exist, the one-side limits have to be in agreement, right? In order for a limit to exist, the one-side limits have to be equal to each other. One side's going towards 7, the other side's going towards 14. They're not moving towards the same y value. The limit doesn't exist. Now we're concluding with our full limit, so there's no plus or minus anymore. We just leave it as 3. Make sure you reference the function. Okay, the function is split between 2 graphs, but we can call it f of x. And we say it doesn't exist. And if the limit doesn't exist, what type of discontinuity are we dealing with? Non-removable. Make sure when you say non-removable discontinuity, you have to specify the point, right? It's not discontinuous everywhere, right? We're only testing at this specific point. All right. So if you guys can continue trying the submit that Word document for and hopefully I can ask teachers as well to see if they have any suggestions. And then tomorrow we'll continue reviewing. I'll have a morning review session tomorrow, 7:45. If you guys have any questions, and then I have another morning review session on Friday. Okay, and if you have any questions, if you want to practice working through this sheet, you have any questions, feel free to send me a text, send me a remind. Okay. All right. See you guys tomorrow. Thanks.
Thank you, Mr. King.
Bye. Have a good day. Bye.
Thanks so much,
Thank you.
Thank you, Mr. Yang.
Thank you. Have a good day.